In this video, we're going to look at patterns in tables of values and how you can recognize what type of function you're dealing with by the pattern in the table of values. Our first function is clearly a linear function, as you can see by the scatter plot. The pattern you'll notice in any linear function is called an add-add pattern. As you go up by the same amount in the x direction, in the x column, you're also going to be either going up or down by the same amount each time in the y column. In this case, you're going up by 2 and down by negative 250. So it's easy to find the slope from the table of values because the change in y is how much you're going down each time, negative 250. The change is x is how much you're going up each time, the positive 2. So slope is negative 250 over positive 2, which is negative 125. To find the y-intercept, you can go backwards in the table. If we added 0 to the table, that means we'd have to go back 2, and it means we'd have to add 250 to get up to the next higher value in the table, 1750. So here's my equation, y equals negative 125x plus 1750. To illustrate, though, another way of finding equations that's going to lead into something we're going to do for other equations, other types of functions, we can also take the two of the points and the general equation, and I want to point out that we're using the general equation y equals ax plus b because our calculator uses a to represent slope instead of m, so I wanted to familiarize you with that. So I'm going to substitute the y value for the y and the x value for the x here, and I get 1500 equals a times 2 plus b, and negative 1250 is a times 4 plus b, using these 2 points. To solve this system of equations to figure out what a and b are, I can subtract the second equation from the first, getting 250 equals negative 2a. The b's cancel out. Or negative 125 equals a. And then I can substitute the negative 125a for a back in the first equation and solve it for b and find out I get 1750. So that's another alternative way to solve the equation. The second function we look at has a different pattern. Notice this looks like it could be maybe power, quadratic, exponential. How do we know which one it is? Well, the way that you can tell that this is an exponential function is that it has an add-multiply pattern. Every time we go up by the same increment adding in the x, we go up or down by multiplying in the y direction. We could multiply by a number bigger than 1, it would increase, or multiply by a number smaller than 1, like a third, and it would decrease. But you see that you have this distinct multiplication pattern. That's always a sign of an exponential function. An exponential function has the equation f of x equals a times b to the x, where b is the base of the exponent and a is the coefficient. Now, if we look at how to find the particular equation, we need to pick 2 points from the table because you need a system of 2 equations to solve for 2 different parameters, the a and the b. Because the x is an exponent here, and it's always helpful to have the higher degree exponent on top when I'm dividing, I'm going to put the second point first. So plugging in 18 for x and 18 for y and 4 for x, I get 18 equals ab to the 4th, and then for the 0.26, 6 equals ab squared. Because I want to eliminate a, I can't do that by subtracting because it's multiplied times the b to the power. So I have to divide instead. I'm allowed to divide because I'm allowed to divide the first equation by the second because 6 equals ab squared. 6 and ab squared equal each other. They are equivalent to each other. So I am dividing the top equation by the same thing on both sides on the bottom, since 6 and ab squared equal each other. So when I divide, 18 divided by 6 gives me 3. ab to the 4th divided by ab squared. A's cancel out. I subtract the exponents, and I get 3 equals b squared, or the square root of 3 equals b. Notice I only use the positive square root because you never have a negative base in an exponential function. Then I can substitute that value for b back into the second equation. I chose that one, and 6 equals a times square root of 3 squared, which is just 3, so a is going to be 2. So my final equation is f of x equals 2 times the cube root of x. Going to our third example, which is actually the fourth example in my notes here, but it's the third example on your notes. Quadratic. When you look at quadratic, you'll notice there's not a real distinct pattern here. If I were to try to multiply, there's no one number I could multiply to get from one value to the next in the y direction. So I tried subtracting, and notice I subtract 8 to get from 30 to 22, then subtract 16 to get from 22 to 6, then subtract 24, then subtract 32. Those numbers have a pattern. From 8 to 16, negative 8 to negative 16 is negative 8, and then from negative 16 to negative 24 is negative 8, and from negative 24 to negative 32 is negative 8. These numbers are all the same. This is known as a constant second difference. Basically, we're applying the linear pattern twice to the y values. When we do that, it's always quadratic. Just as a note, if we were to do that pattern 3 times and then they all ended up the same, it would be cubic. Or if we did that pattern 4 times until they all ended up the same, it would be an x to the 4th equation. So looking at my general equation, f of x equals ax squared plus bx plus c, there are 3 different parameters that I have to find, a, b, and c, which necessitates 3 equations. So I'm going to pick the first 3 points, substituting the x values in for x here and the y value in for f of x. So 30 equals 4a. Now where did I get the 4a? Well, x squared would be 2 squared, so that would be 4a. b times x, b times 2 would be 2b plus c. Notice there's nothing squared down here because the squared part is a number that I'm inserting. Then 22 equals 4 squared times a, 16a, plus 4 times b plus c. 6 equals 6 squared times a, 36a, plus 6b plus c. To solve this system of equations, I select the first 2 equations and multiply the first one by -1 so that I have opposite values for c. And then when I add the 2 equations together, the c's drop out and I get -8 equals 12a plus 2b. Now I want to create another equation with a and b in it so I can get rid of the b, so I pick a different pair of equations. So I picked number 2 and 3, multiplying the equation number 2 by -1. So those are down here. And notice when I add them together, the c's drop out again, getting -16 equals 20a plus 2b. Now I'm going to take these 2 equations, the one in the red box and the one in the blue box, and combine them together. So I'm going to take the one in the red box, multiply everything in it by -1, so both sides of the equation by -1, which gives me positive 8 equals -12a minus 2b. Add that to the equation in the blue box, and that gets rid of the b's. Now I have -8 equals 8a, or -1 equals a. I'm going to substitute -1 equals a back into this red equation. I could substitute it into either of the equations, but I'll just pick that one, which I did over here. So 8 equals -12 times -1 minus 2b. Solving that for b, I end up with 2. So now I have a equals -1 and b equals 2. I'm going to take both of those values and put it in this first equation down here, and then I wrote that down here. 30 equals 4 times -1 plus 2 times 2 plus c. So 30 equals -4 plus 4 plus c, c equals 30. Now I have a, b, and c. I go back looking at my original equation. I guess I wrote it down here. There's my general equation. I know what a, b, and c are now. I substitute in -1, 2, and 30, and there is my quadratic equation. Now the 4 equations I'm going to ask you to be able to do are linear, quadratic, exponential, and power. Linear and exponential are the easiest to spot. Look for linear first. If that's not linear, check for exponential. Look for that add-multiply pattern. If it's not either of those, check for quadratic, that constant second difference. If it's not quadratic or linear or exponential, then it's going to be a power function. So let's look at a power function up here. A power function has kind of an unusual pattern in that first of all, you notice it's not exponential. It kind of looks like it's going to be, but I do 2,000 divided by 4 and I get 500, but 500 divided by 4 doesn't give me this 222, which I just crossed out, and I'll explain that in a minute. But if I divide 500 by 4 again, I get 125, which is down here. It turns out we have a multiply-multiply pattern. If I multiply the x's, 2 times 2 is 4, 4 times 2 is 8. Notice I skipped over the 6. Notice here I skipped over the 222.2 repeating. So I just crossed that out to show not that it's not a point on the graph, but that it's not included as part of my pattern. If I continued the pattern, I'd do 125 divided by 4, and I'd get 31.25. And 8 times 2, and I'd get 16. So I'd be skipping over several of my values in the table. That is the power pattern. Notice the power equation is very similar to the exponential equation. Instead of ab to the x, it's ax to the b. So I'm going to solve it in a very similar way. I'm going to pick 2 points, once again putting the one with a higher x value on top, substituting 500 for y and 4 for x, which is now the base. So 500 times equals a times 4 to the b. 2,000 equals a times 2 to the b. Dividing the second equation by the first, or the first equation by the second, I get 500 over 2,000 equals a times 4 to the b over a times 2 to the b. The a's cancel. 4 to the b divided by 2 to the b is the same as 4 divided by 2 to the b. Same exponent, I can divide the bases. So 1/4 equals 2 to the b. Many of you will recognize at this point that b is -2, which is fine. However, sometimes you'll end up with messier numbers that you won't be able to recognize. So in this case, you would have to use logs to solve. So I went through the process of using logs to solve for b. So once you know what b is, you can plug it back in to one of the equations. So I plugged it into the second equation and solved for a down here. Now I know a, I know b, and I can write my equation. That's the power function. So your homework is going to be involved looking for these patterns and writing equations, checking them on your calculator, and the calculator instructions are posted. Make sure to look at those if you have any trouble. I may put a video up about those if I have time. And there's going to be messier numbers in your homework though, including a problem that has some real world data in it. And so recognize that right now all of our graphs and our equations are perfect because these are just the table of values for this equation. But if you're given data and asked to write an equation for data, it might not turn out so perfectly and your numbers might not be nice numbers. You might end up with crazy decimals for your A's and your B's. That's perfectly okay. There's nothing wrong with that. So just be forewarned. There you go, writing equations from patterns in data.